Okay, so previously we talked about converting the numbers from decimal to binary, and then we saw a case where we have a non-terminating number when we convert it into binary, and we said we have to stop at some point, and that point is basically based on how many bits I have allocated for my fraction bits. So to build up on this, there's, like I said, there's two ways. We'll cover two ways that represent values that are non-integers in binary. One is called the fixed point representation, and one is called the floating point representation. So in this video, I will talk about the fixed point representation. And essentially, fixed point is a way to say allocate a certain amount of bits for the fraction part of the number and a certain amount of bits for the integer part of the number. So let's say I have a number in binary that is 8 bits. Now, one way to use those bits is to allocate all of them for the integer. So I will have 1, 2, 3, 4, 5, 6, 7, 8. All of them will be for the integers, which means I can not represent any fractions with this representation. On the other hand, I can also do the 8 bits, I can allocate all of them for the fraction. So rather, it's here. Now, in this case, I can represent a lot of fraction values, but I can represent no magnitude. There's no integer part for it. The other way is to allocate some of them for the fraction and some of them for the integer. And for example, one way I can do for half and half, right? So I can do 1, 2, 3, 4. 0.1234, which means I have 4 digits that represent the fraction and 4 digits to represent the integer, the I bits. Now, this is all good, but there is also more to it. Well, what if I want to represent negative values? So this representation allows me to represent, so the maximum number, for example, in this case will be 1, 1, 1, 1. That's the largest value I can do. 1, 1, 1, 1. And let's say this is all positive, then I can represent the maximum 15 point whatever these numbers are, the sum of these numbers are. But what if I want to do a signed number? Then I will have to allocate 1 digit for the sign, then maybe 3 digits for the integer and 4 digits for the fraction. So if we are using this notation, they call this an unsigned. So the notation for that is U, unsigned 4, 4, which means that I have 4 bits for the integers and 4 bits for the fraction. And if I do care about the sign and I want to represent negative values, then I can use a signed fixed point representation. I have 3 digits for the integer and 4 digits for the fraction. So this is called the fixed point representation, and it's just a way to indicate, if you're looking at a number in binary, how many bits are used for the fraction and how many bits are used for the integer. So I'll show you a few variations. I'll just do a couple of examples. For instance, if I have like U, let's say 8, 8, this means that the number has allocated 8-bit for the integer part and 8-bit for the fraction, and there is no sign bit. So this is all no sign bit, which means that all the numbers here represented this representation are positive. On the other hand, if I have an S, let's say 7, 8, this means that the number I'm looking at is or has 7 bits for fraction, for integer, sorry. I have 8 bits for fractions, for fraction, and 1 bit for the sign. Okay. Obviously, those numbers can be any combination depending on what the situation calls for. You can have an 8-bit number represented with fixed point representation. You can have a 4-bit number, you can have a 16-bit number, 32-bit number, 64-bit number, and so on. For example, you can have an unsigned number that is 16-bit for the integer and 16-bit for the fraction. So this together, there's 32 bits for the number to be represented. So let's do a quick example. Let's say I want to convert, let's say convert 10. Well, let's not use 10 because it looks like binary. Let's just say 9.625 from base 10 into binary using unsigned representation of for, let's say, 8, hypothetically. So first step to do would be to actually convert the number itself into binary. So the integer part, 9, is going to be represented as 1001. Hopefully you guys know how to do this rather quickly. And then my 0.625, I have to convert it into binary. So I'll do this example one more time. 0.625, let's see, yeah, 0.625 times 2 is 1.25. I have a 1 here. Then I take the fraction part, 0.25 times 2, I get 0.5. 0.5 times 2 is 1.0. I'm done. And these are my 3 fraction bits. So 0.625 equals 0.101 in binary. Now I need to place these values in that unsigned for 8. So my unsigned for 8, like I said, has 4 digits for the integer, followed by the radix point, and then 8 bits for the fraction. 1, 2, 3, 4, 5, 6, 7, 8. So we said we got the 9 was 1001, and then the fraction was 101. And obviously the remaining bits here to the right are all 0. So 0, 0, 0, 0, 0. And this number is 9.625 in fixed point representation as unsigned 4, 8. Now here's a follow-up question. Can I do the same thing using signed digits? The answer is yes. But actually, let me give you another example going the other way around. So let's say I have the unsigned number of, or let's say it's unsigned 7, 9 of, so I have 7 digits for the integer, 1, 2, 3, 4, 5, 6, 7, and then 1, 2, 9 for the fraction, and the value I have here is 0, 0, 1, 0, 1, 1, 1, and then for the fraction part it's 0, 0, 0, 1, 0, 1, 0, 1, 1. Now I want to convert this to decimal. Okay, there is no sign bit, so I'll treat this number as a positive number. And I go about doing it the way we have done these kind of examples in the previous video. So let me just move this out of the way so I can write here. All right, so this is 2 to the power of 0 times 1, which is 1, plus this is 2, plus 4, this is a 4, this is 8, I don't need it, and then this is 16. Then plus point, then here, this is 2 to the negative 1, 2 to the negative 2, 2 to the negative 3, 2 to the negative 4. So this is 1 over 2 to the 4 plus 1 over, this is 5, 6, 1 over 2 to the power of 6 plus 1 over, This is 7, I don't need it. This is 8 to the power of 8 plus 1 over 2 to the power of 9, which is equal to, if you add these up, you get 23 point, see, 1 over 16 plus 1 over 64 plus 1 over 256 plus 1 over 512. You don't need actually to put this here, you'll get the fractions right away anyway. And if you add these up, you'll get 23.08398 4375. This is the number in base 10. So if technically speaking, if you have this number in memory, stored in memory, and the system is treating this number as an unsigned 79, the value that it will understand will be 23.083984375. Okay, what if I told you that this number is not unsigned, it's actually signed? Will that change anything? Well, the answer is actually yes, but let's just to be consistent, let's say I have the same exact number, but instead of unsigned 79, I have signed, and I have 69. So both numbers are actually 16 bits. That means the first bit I have, let's do it here. I don't need that. Hopefully I can fit everything here. So again, I have 1, 2, 3, 4, 5, 6 dot 1, 2, 3, 4, 5, 6, 7, 8, 9, and the same value. So 0, 0, actually, 0, 0, 1, 2, 3, 4, 5, 6, and I have 1 bit for the sign. Okay, so okay, and then the same thing here, 0, 0, 0, 1, 0, 1, 0, 1, 1. Now, will that change? So this is a signed 6, 9 number of this value. The only difference here is that the first bit that I have here is going to give me the sign. And a 0 means the number is positive. Now, the remaining bits will be the same, right? So you treat it just like a regular binary number. So we said this value turned out to be 23, and then this value turned out to be 0.8398437.5. So there is no real change here. But what if I have a negative value? Like what if the sign bit here is actually negative or 1? What do I do? Well, you follow the same steps, but then you do you take the 2's complement of that number to find the actual value. So let's do another example. So let's say I have the signed number of 8. This is the representation, sign 87. This is a 16-bit number. You have 8 bit for the integer plus 1 bit for the sign, so that's 9 bits, and then 7 bits for the fraction, so that's altogether you have 16-bit value. 1, 2, 3, 4, 5, 6, 7, 8, 9. Then 1, 2, 3, 4, 5, 6, 7. And that number happens to be 1, 0, 1, 1, 0, 1, 1, 0, 1, 1, 0, 1, 0, 1. I'm off by 1 bit. 1, no, 0. That's right. And then 1, 1, 1, 1, 0, 1, 0. The question is like, how much is this in decimal. I'm going to convert this to decimal. Okay. So I take a look at the sign bit, and the sign bit is 1, so that means the number is negative. Now, my number is 0, 1, 1, 0, 1, 0, 1, 0. And as you know, how do I evaluate negative numbers? You take the 2's complement of the number to evaluate it. So the number that I have, so now, like I said, this bit is gone. This is the sign. So what I have remaining is 0, 1, 1, 0, 1, 0, 1, 0, 0.1111, So to take the 2's complement, what you do is you flip the bits, 1, 0, 1, 0, 0, 0, 0, 0.1010, 1, 0, 0, 1. Then you add 1 to this. Get 0, carry 1, 1, 1, 1, 2, 3, 4 zeros. 1, 0, 1, 0, 1, 0, 0, 1. You evaluate this, you get, this is 1 plus 4 plus 16 plus 128 plus 1 over 2 to the negative 1, 2, 3, 4, 5. So this is 5 to the power of 1 over 2 to the power of 5 plus 1 over 2 to the power of 6, which is 149 plus 1 over 32 plus 1 over 64, which is 149.046875 base 10, and the number is negative, so that is the value of this binary 16-bit binary number using signed 8,7 representation. All right, so to summarize, in this video we talked about representing the values using fixed point representation. We started with talking about what makes a number in memory a fractional or non-integer. Basically, when the number has some of the bits being allocated for the fraction and some of the bits allocated for the integer. And then we said there is an unsigned representation. We had an example of unsigned 8,8. We had another example of signed 7,8, which makes the number basically still a 16-bit number and has 1 bit for the, it has 1 bit for the sign, 7 bits for the integer, and 8 for the fraction. And then we did an example that we wanted to convert 9.625 from base 10 to unsigned 4,8, unsigned fixed point representation. And then we did another example where we had a signed representation. Actually, was the build-up for it. So this was signed, but the signed bit here was 0, so the number had no change. And then we did one where the sign was 1, so we did a conversion from signed 87 to decimal. And the way we do it is we take a look at the sign. If the sign bit is 0, that number is positive, you just convert it. If the sign bit is 1, you treat it like a negative number, and to convert it to decimal, you take the 2's complement, and you get your answer. Thank you for watching.